Right, chapter 2, section 4, continued. So we'll do pages 1 and 2 of the notes in this video. The average rate of change of a function. Now, we already saw the difference quotient. And this is similar because it really is slope. And the difference quotient was a quotient. It was a ratio. It was a ratio of two things. Like slope. Average rate of change of a function. And that difference quotient, that was, we found the difference quotient when we were given the two function equations. Well, actually, it was one function equation. You had to evaluate the function at f of x plus h. This is a little bit different. This, we're going to find the average rate of change, which, again, is still slope of a function when we're given, say, two x values. So the most common rate of change that we're familiar with for linear functions, again, is slope. And we talked about that when we talked about the difference quotient. If the graph of a function is not a straight line, we speak of an average rate of change between any 2 points on the graph. So it's an average rate of change. All right, so we have a diagram on the note sheet here. I'll talk about that in a moment. To find the average rate of change, we must calculate the slope of the line that contains the 2 points. And that line is called the secant line. Secant line is a line that passes through 2 points, if you remember from geometry. All right. Also from geometry, if you remember, the tangent line is the one that just touches or bumps up against it. But this is not a tangent line. This is a secant line, passes through 2 points. So here, let x sub 1, comma, f of x sub 1, and x sub 2, comma, f of x sub 2 be distinct points on the graph of the function f. And we can see that here in this diagram. This is x, the value of x sub 1. This is the value of x sub 2. This ordered pair right here would be x sub 1, comma, f of x sub 1. And there's my x sub 2, comma, f of x sub 2. Folks, these are just ordered pairs. x1, y1. It's in function notation. And this is x2, y2. And we can use those to find the slope. So the average rate of change from x1 to x2 is this. Change of y over the change of x. Okay, delta y over delta x. These are the y's, f of x sub 2. Remember, f of x takes the place of y. All right, so here is my function. I know it's a function. It passes the vertical line test. All right, that's my function. These are my two ordered pairs, and when I draw a line through them, I can find the slope of that line using those values. Now, of course, we're going to know the x's. We don't know the y's. We're going to have to calculate it, and you're going to see that in the next example. All right, here. Y equals f of x. There's no values on here. It's just textbook notation. All right, if you have any questions on that, you know what to do. Post on the discussion or ask in class. All right, here's what we're going to do with this. Find the average rate of change of f of x equals x cubed from 3 parts here. 0 to 1, from 1 to 2, and from -2 to 0. We're actually going to do this algebraically And then we're going to look at it graphically and compare our results is what we're going to do here right now. All right, so find the average rate of change. I like to either circle or highlight my function because sometimes these are more than one term. This one here happens to be just one term, x cubed. But sometimes there's more going on, and so you're going to want to circle or highlight the whole entire function equation. All right. What do I have? I'm given the function, and I'm given two x values. I have to compute and find the y values. I have to find f of x sub 1, and I have to find f of x sub 2. Right? I'm really finding f of 0 and f of 1. F of 0 and f of 1. So I'm going to use my function to do that. It's something cubed, something cubed. The something is 0 and this something is 1. 0 cubed is 0. 1 cubed is 1. Does it always work out this way? No. All right. My slope formula is really y2 minus y1, written in function notation, over x2 subtract x1. F of x sub 2 is 1, subtract. F of x sub 1 is 0. X sub 2 is 1. X sub 1 is 0. This is 1 minus 0, which is 1. Same thing in the bottom. And so I see that the average rate of change on the x cubed function from 0 to 1 is 1. So the secant line has a slope of 1. Okay, we're going to do the same thing for parts B and C. Again, what do you do with these types of problems? Well, you have to compute, you have to find the y's. F of x sub 1, f of x sub 2 is really finding f of 1 and f of 2. F of 1 we know is 1 cubed, which is 1. F of 2, remember I'm getting this from the original function. I'm going to cube a 2 and get 8. All right, now notice, from 0 to 1, my slope was only 1. I'm clearly seeing that something bigger is happening here from 1 to 2. So it's appearing as though there's a much steeper slope on this one. F of x sub 2, subtract f of x sub 1, that's really my change of y. Over change of x, f of x sub 2 is 8, subtract 1, over the originals, 2 subtract 1, 8 subtract 1 is 7, 2 subtract 1 is 1. Average rate of change now on the graph of the cube function from 1 to 2 is much steeper. The slope is 7. We'll see what happens from negative 2 to 0. Again, you have to compute the y values by actually finding f of negative 2 and f of 0. When I cube a negative, it's negative. When I cube a 0, it's still 0. All right, set up. I like to write my formulas over again because I feel like I learned them better because I have memories of writing it over and over and over again. Would you be given this formula on a test? I don't think so, because you would just have to know that this is slope. So it's change of y over change of x. They give you the x's, you have to find the y's to be able to do this. All right, f of x sub 2 is 0. Subtract, what is f of x sub 1? That's negative 8. What do we got for our x's? 0, subtract, negative 2. This is 8 divided by 2, or 4. So the average rate of change on the graph of the cube function from negative 2 to 0 is 4. All right, so now what we're going to do is graph this and actually show you and prove that this is true. All right, so for the 3 graphs, we are going to graph 3 times. F of x equals x cubed. F of x equals x cubed. F of x equals x cubed. I like to graph it 3 times. Later on, we are going to get into graphing and transformations of functions, and it would behoove you to know the ordered pairs on the cube function. All right, a no-brainer. 0, 0 is on it. You know, 0 cubed is 0. 1 cubed is 1. Negative 1 cubed is negative 1. So those 3 dots on the diagonal are always on the cube function, the parent function of the cube function. In other words, there's no transformations, no moving up, down, left, right. Okay, so your basic cube function has those 3 points as ordered pairs. And then I'm going to choose 2 more because, you know, this looks like a line, and it's not. It's the cube function, x to the power of 3. Now I'm going to take a 2 and cube it, and I get 8. We saw that up here. 2 cubed, oops, right here. 2 cubed is 8. So I'm going to go where x is 2, and I'm going to go up 8 units. 1, 2, 3, 4, 5, 6, 7, 8 up here. And negative 2 cubed is negative 8. So I'm at 1, 2, 3, 4, 5, 6, 7, 8, somewhere about there. All right, I'm going to do the same thing over here. 2 cubed is 8. Negative 2 cubed is negative 8. 2 cubed is 8. Negative 2 cubed is negative 8. I'm now going to connect. Cube function takes on this look. Okay, we're going to do it 3 times. And 1 more time. All right, there are my 3 graphs for the cubes. Now, I'm going to draw the secant line. The first graph was from x1 equals 0 to x2 equals 1. I'm going to put a dot here and a dot here. I'm going to draw the secant line that connects those 2 points. And now I'm going to look at the slope of this line. From this point to this point, I rise 1 and run 1. Rise and run 1. Rise and run 1. So guess what? The slope of this is 1, which matches the algebraic computation of the slope of the secant line. All right. From, maybe I should do this one in a different color. From x1 equals 1 to x2 equals 2. All right, so where x1 is 1 is here, where x2 is 2 is here. And I'm going to draw my secant line and calculate the slope. From this point to this point, I'm going to rise 1, 2, 3, 4, 5, 6, 7, and run 1. The slope is 7 over 1, or 7. And again, that matches what we found algebraically right here. Last one, I'll go back to the green. From x sub 1 equals negative 2 to x sub 2 equals 0. All right, so which point is x is negative 2? This one down here. And 0, that's this one here. So I'm going to connect those 2 points, draw my secant line, use my rise over my run. So from this point to that point, I'm rising 1, 2, 3, 4, 5, 6, 7, 8, and I'm running 1, 2. That's 8 over 2, which is what we saw here. That's 4. So really, all you're doing is finding the slope of the secant line, and that's giving you the average rate of change of a function. If you have any questions on it, please ask. The next part here of the video, that the lesson that we're going into, is odd and even functions. Folks, we do a lot with odd and even in this course. So pay attention to that. I'm going to show you the algebraic way, which is the preferred method of use. And then I'm going to show you the easy way after I go through the algebraic. All right, the function of f is an even function. We're going to want to know later on. You're going to have to graph using leading coefficient test, and you won't be able to use a graphing utility to do this. And we need to know, is the function even or odd? Because the end behavior of the graph depends on knowing whether the function is even or odd. And then later on, we're going to talk about the leading coefficient, whether it's positive or negative. So if we look here, in the cube function, the ends of the graph are going in opposite directions. We're falling on the left and we're rising on the right. If you think of a parabola, okay, the parabola, which has this shape, okay, the parabola, the ends of the graph go in the same direction, either both up or both down, okay? So it's important for us to know what we're talking about when we are thinking about odd and even functions, because it's going to have a practical use for us later. All right, so the function of f is an even function if f of the opposite of x equals f of x for all x in the domain of f. All right, so what do we do? When evaluating f of x at f of the opposite of x. We did that, okay? Remember, you had to evaluate f of 2, f of x minus 1, and then f of the opposite of x. So when evaluating the function at f of the opposite of x, you will get the same function. And we're going to see that when we do practical examples down below. You get the same function result. That happens if the function is even. So if even, you get the same. The function of f is an odd function. If f of the opposite of x equals the opposite of f of x for all x in the domain of f. Let me underline that in purple. So when evaluating f of x at f of the opposite of x, you will get the opposite function. You know, when you take the opposite of x, it's negative x. When you take the opposite of 2, it's negative 2. When you take the opposite of x plus 1, it's negative x minus 1. So you're going to get the opposite function out. And I always remember it, you know, O for odd. You know, it starts with the letter O. Comma, O for opposite. All right, now if I look at this notation, I mean, really, think of this logically. When the x's are opposites, the y's are the same, right? So if I cover up, like, you know, this negative x and this positive x, I see positive f equals positive f, right? So when the x's are opposite in sign, the y's are the same. But here, when the x's are opposites in sign, the y's are also opposites in sign. We see that up here, the cube function is an odd function, right? It's power of 3, and 3 is odd. So if I'm looking and comparing these two ordered pairs, this ordered pair is 2, 8, and this ordered pair is negative 2, negative 8. So when the x's are opposites, so are the y's. Okay, and that's what's going to happen. And that's really what this means here. But if you're asked to compute this algebraically, this is really what you're going to do. Identifying each of the following functions as even, odd, or neither. So if neither one of these things happen, then you have to say the function is neither even nor odd. All right, number 1. All right. Apparently my last video got messed up and I had to splice these two videos together. Back to this. Identifying each of the following functions as even, odd, or neither. So I've got my first function, f of x equals x squared plus 6. I'm going to evaluate this function at f of the opposite of x. Now my original function is x squared plus 6. So I'm going to leave a space and put the negative x squared in there so that I can evaluate f of the opposite of x. So f of the opposite of x, now when I square a negative, it goes positive, plus 6. And now I'm looking and comparing this on the right side of the equal signs. They're exactly the same. Nothing changed. So when I evaluate f of x at f of the opposite of x, and I get the same output, the function is even. So we'll say, since f of the opposite of x is exactly equal to f of x for all x in the domain of f, the function is even. The next one, we're going to do the same thing. We're just going to take each one of these functions and evaluate at f of the opposite of x and compare the output. So here, this is a g function, so I'm going to evaluate g of the opposite of x. I'm going to set it up. The original is 7x. I'd leave a space, you know, for the x. And then I'm going to substitute the negative x inside. And now I'm going to actually simplify this. G of the opposite of x equals, well, when I cube a negative, it stays negative. So this is negative 7 times x to the power of 3. And then here is the opposite of a negative. That's positive, plus x. You can compare it here, you know, when I look, g of x and g of the opposite of x. 7x cubed, this is negative 7x cubed, this is negative x, this is positive x. So when all of them have opposite signs, that means it was changed. And in fact, I'm going to rewrite it like this and factor out that negative. So I get a 7x cubed subtract x. Now if I look here, 7x cubed subtract x is inside my group, but there's a negative outside. All right, so again, I'm comparing these. You could either do it here at this step or here. If you do it at this step, you have to make sure all the signs changed. All of them became opposites of what you had in the original. Or factor out the negative and do a comparison. This and this is the same, and here's where the opposite happens. But the bottom line is since g of the opposite of x is equal to the opposite of g of x, the function is odd. All right, move my paper over a little bit. All right, so one more time, up here. I compared the two, the output, right? The output is the y. F of x takes the place of y. All right, so I compare the right side, x squared plus, it's exactly the same. So since f of the opposite of x equals f of x, the function is even. Folks, we're saying that when the x's are opposites, the y's are still going to be the same. And that's true with an even function. And since g of the opposite of x equals the opposite of g of x, then the function is odd. So what's really happening here is when the x's have opposite signs, so do the y's, right? Because, you know, g of x really is y. So this would be y equals negative y. And if we look back on our cube function that we did above on the top of the notes, and we look at these ordered pairs, this is an odd function. You know, this is the function f of x equals x to the power of 3. It's an odd function. And I'm going to tell you the easy way of how you can tell just by looking at the equation if the function is even or odd. I'm going to go over that in a few moments. But up here and here, if I look, when the x's are opposites, so are the y's. Okay, so here I have 2 and negative 2 and 8 and negative 8. So when both the x's and the y's are opposites, then the function is odd. And that's what we are, talking about here. When the x's are opposites and the y's are the same, function's even. When the x's are opposites and the y's are opposites, the function's odd. The last one is going to be a situation where neither thing is true, which you should expect. Because we did the even, then we did the odd, and then we're going to do the neither. So I'm going to arrow down here. I'm going to evaluate h of the opposite of x. I'm going to set up my template, x to the 5th plus 1. I'm going to substitute the opposite of x in there. And now I'm going to simplify this. A negative raised to an odd power is still negative, so that's negative x to the power of 5. This one does not change. So, you know, h of the opposite of x equals this. Folks, we're comparing h of x and h of the opposite of x. Are they the same? Well, no, the one is the same sign, but the x term changed signs. If I were to take it a step further and factor out that negative, that would be positive x to the power of 5 minus 1. It's still not the opposite. It's just not, because this part now, x to the power of 5 plus 1, is now x to the power of 5 minus 1. So they're not the same and they're not opposite. Okay, because this is not the same and this is not the opposite of that. So this is a situation where neither, since we'll say h of the opposite of x is not h of x or the opposite of h of x. Right? Neither condition is true. The function is neither even nor odd. Okay, so that's a neither situation, because when I evaluated function at h of the opposite of x, I didn't get the same output, and I certainly did not, when I compared these, I didn't get the opposite output either. All right, this is how you would do this algebraically. Now, I'm going to show you a shortcut, and you may use the shortcut on a test or a quiz, but you have to show the work for the shortcut on a test or a quiz. Do not use the shortcut if you don't understand the shortcut. So what I'm going to do in the margin over here is I'm going to recopy the f of x equals x squared plus 6, the g of x equals 7x cubed, subtract x, and the h of x equals x to the power 5 plus 1. Now, what you need to understand and be able to remember to do here is that every term in your polynomial has to have a variable. All right, so this is a quadratic term, and this is a constant. It doesn't have a variable. But I can put a variable in there. You know, if I insert an x here, that's my variable, but it can't be x to the power 1 because x squared plus 6 is not the same as x squared plus 6x. So I need some exponent on x that's not going to change this number from being a 6 originally. Well, 6 times 1 is 6, and x to the power of 0 is 1. And so that's how I can trick it. All right, so this becomes x squared plus 6 times x to the power of 0. This has an x. It doesn't have the exponent there, but you could write it. Write the 1. And this here, I have x to the power of 5 plus 1. Again, this is a constant. So for each time you have a constant term, you want to insert an x to the power of 0 right next to it. All right, so momentarily I'm going to show you the trick of how to show if a function by looking at its equation is an odd, even, or neither odd nor even function is by just by looking at their exponents. But there's one thing that you have to understand, okay? 0 is a very strange number. Really easy to work with, difficult to understand. It's smack dab in the middle of the number line separating my negatives and my positives. So why doesn't 0 have a sign? I don't know. That's a property that's kind of out there as well. All right. Well, I mean, there's a philosophical reason, but you would have to investigate that. It's long. It's drawn out. The very easy thing saying is I got nothing. So I don't have one and I don't owe one. I got nothing. Okay, so we could think of it in terms of that with the signs. But what you have to be willing to accept is that 0 is an even number. I mean, just for the very fact that it is sandwiched in between two odds. And on the number line, every other number, it switches even, odd, even, odd, even, odd, right? -3 is odd. -2 is even. Then this is odd. That's even. Odd, even, odd. So 0, convince yourself or memorize, 0 is even. It's between two odds. All right, so now that you know that and you've got that, we're back to this. Just look at the exponents now. And you can do this on a test or a quiz. Learn the quick, short way. But you'll have to show me work, and the work is what I'm going to show you in a moment. You could do this way, the algebraic way. But I'm going to do it this way. So I look and I say all of my terms in the polynomial have to have a variable. And if it's a constant, I'm going to put an x to the power of 0 there. Now I'm going to look at all of the exponents, all of the powers on the exponents. 2, that's an even number. 0, that's also an even number. And if all the exponents are even, the function is even. This would be the work that I would be requiring you to show me on a test or a quiz. All right, so since all of the exponents are even, the function's even. And we saw that here. The function was even. All right, the next one. I'm looking at the exponents. This one had a variable. I just couldn't physically see the exponent, so I wrote the 1. The 3 is odd. The 1 is odd. If all of the exponents on the variables are odd, then the function is odd. And lastly, I'm looking at this last example again. There was a constant, so I had to slide in an x to the 0 power here. This exponent is odd. This exponent is even. Folks, we can't be even and odd at the same time. So the function is neither even nor odd. So, if you like the easy way, learn how to show the work the easy way. Remember that you have to slide in an x to the 0 power there. And then, compare the exponents. Well, look at the exponents and determine if they're even or odd. So this would be enough work to show me that I know you know function is even, odd, or neither. All right, that ends this part of the section. If you have any questions, you know what to do. Contact me somehow, whether you're in class or on the homework discussion or in a Google Meet. Have a great day.